One moment. Just taking a minute to load. And okay, there we go. So this is the week 13 review for Math 2417. In this review, we'll cover some more trig integrals, specifically some integrals involving some products of trig functions. Then we'll get into trig substitution, which is a really neat way to solve some integrals. And lastly, we'll talk about partial fractions. So let's jump right in. Some trig integrals. And the first thing we'll do is talk about some trig identities, because these things are at the root of how we solve these integrals. First off, we've got our Pythagorean identity, sine squared x plus cosine squared x equals to 1. Then we also have a couple of double angle identities. So sine squared x equals 1 minus cosine 2x over 2, and then cosine squared x is 1 plus cosine 2x over 2. So these identities help us to solve integrals specifically of the form like sine cubed x cosine squared x dx. For instance, we can't solve this in this form using u substitution, because if we let u be equal to sine, then du would be cosine, but we would only have one cosine. But here we have a cosine squared. So we need to figure out a different form or a way to rewrite this integral so that here. And my computer's all frozen up. It's not doing this. I will be back in a couple minutes. Sorry about this. Alright, sorry about that. For some reason my writing tablet occasionally just doesn't communicate right with my computer and it just freezes up. So, all right. Hopefully it doesn't happen again. But no, we'll just keep going. As I was saying, this integral, you need to rewrite it in a new form so that we only have one sine or one cosine so that we can use U substitution. And in this case, we're going to, the sine cubed is like the sine of x times sine squared x. So we can actually take out this sine squared x and replace it with the cosine squared x. So this integral is exactly equal to sine of x times 1 minus cosine squared of x, because this part is equivalent to sine of x. Let's make a note of that right there. Sine squared x. And then we still have our cosine squared x dx. And from here, we just need to continue to simplify. So we have the integral sine of x times 1 times cosine squared x is sine x cosine squared x dx. And we have minus the integral of sine x times cosine squared x times cosine squared x. So that's sine x cosine to the fourth x dx. And then in both of these cases, we can let u equal to cosine of x. So then du is negative sine of x dx. And then this would become negative the integral. Oh boy. Come on. Oh boy. Alright, I'm sorry about this. I think I'll just have to end up doing some drawing on the screen for the rest of the session. Be right back again. I cannot see your messages, by the way. Alright. So sorry about that. I think I'm just gonna have to stop using my writing tablet for the rest of the session. Because that is typically what causes the problems. So hopefully my handwriting doesn't get too bad. Alright. So again, we've got u and du, so this becomes negative. Different whiteboard. Alright. Now we're at the point the integral of x cosine squared x dx minus sine to the fourth cosine squared x sine of x sine to the fourth x dx. If we let u equal to cosine x, then du is negative sine x dx. So this is negative integral squared du. How did I get these two integrals? These were from the previous, let's see, I can still share the previous work. So, from the previous portion, what we had was we'd worked up to this point. We started with this integral, the integral of sine cubed x cosine squared x. Then we used a trig identity, sine squared plus cosine squared equals to 1. We rearranged it to say that sine squared x is 1 minus cosine squared x. And then we took out a sine squared x from the sine cubed, leaving us with sine x times 1 minus cosine squared x times cosine squared x. And then we just distributed. Does that make sense? You're welcome. Now, back to this other board. This becomes the negative integral of u squared du plus the integral of u to the fourth du. So this is 1 minus 1/3 u cubed plus c. And since u was cosine of x, that's 1/5 times cosine to the 5th x minus 1/3, not sine, sorry, minus 1/3 cosine cubed x plus c. And that would be our answer for the first problem. Makes sense? Cool. For our next one, be a little different. It's going to look very similar though. Sine squared of x, that is a 2. Of x cosine squared x dx. Well, with this one, what we can do is if we tried to use the same substitution and say that sine squared x was equal to 1 minus cosine squared, the issue with that is then when we take out our sine squared, all we have are cosines. So we can't let u be equal to cosine because then we don't have a du, which would be sine. The trick to this one is using one of the other trig identities that cropped up. That was that sine squared of x was equal to 1 minus cosine 2x over 2. So then if we substitute sine squared of x out, we're left with the integral of 1 minus cosine 2x divided by 2 times cosine squared. But since the cosine squared of x has a different number in the inside, for instance, this is cosine of just x. This has a 2x on the inside. We actually want to convert the cosine of x into a cosine of 2x as well. And if you recall, that identity was cosine squared x is 1 plus cosine 2x over 2 dx. Then we simply distribute. We get that it's the integral of 1 minus cosine squared of 2x over 4 dx. And then we can simply break it apart around the apologies, around the numerator. So we can say it's the integral of minus 1 over 4 integral cosine squared 2x dx. So the integral of 1/4 is easy. The integral of cosine squared 2x is a little more difficult, but we actually just want to use the same identity we did here again. So we can say that cosine squared of 2x this time is equal to, well, we still have our 1/4 dx, but this time the integral of, cosine squared 2x would be 1 plus cosine of 4x this time over 2. So we have minus 1 over 8 integral 1 plus cosine 4x dx. And these we can just apply our basic integration rules on. So we're left with 1/4 x minus 1/8 x. The integral of cosine of 4x is 1/4 sine 4x, so we have minus 1 over 32 sine 4x. So 4 plus c. So then we simplify these first two terms, and we're left with 1 over 8x minus 1 over 32 sine of 4x plus c. Any questions? Cool. All right. Go ahead and try. This one's going to be a little bit different. Well, actually, it's going to be similar to the first example. Go ahead and try working out the integral of sine of x cosine squared x dx. And I'll go ahead and give you a hint. You might want to consider trying to reduce sine down to sine to the first power of x using your Pythagorean identity. So using that sine squared x plus cosine squared x is equal to 1. Go ahead and try that one out, and I'll give you a few minutes to work on it. All right, how's it coming? One-third cosine cubed of x minus 1/2 cosine to the 4th of x plus 1/5 cosine to the 5th of x plus c. All right, well, let's work through it and see what happens. So, try and zoom in just a bit more. So that way we can get a little more space to write with. I'll go ahead and decrease the brush size as well. All right. So we start with sine to the 5th cosine squared. And we can rewrite that as sine of x times 1 minus cosine squared of x squared, because this is sine squared squared. So sine to the 4th times sine of x gives us sine to the 5th. And of course, we still have cosine squared of x. Next, we can go ahead and simplify this integral by distributing the 1 minus cosine squared squared. So we get the integral of sine x times cosine squared of x. Yeah, it looks like you maybe missed one term or two. Yeah, did you just do 1 minus cosine squared and not 1 minus cosine squared, then that squared? That would be my guess. So, moving on from here, we have times cosine squared x dx. That would be if we distributed this one to itself, because we've got 1 minus cosine squared times 1 minus cosine squared. Then we would have minus twice the integral of sine of x cosine to the 4th of x dx. And then finally plus the integral sine of x cosine to the 6th of x dx. And then all of these we can simply solve with u substitution. So the integral of sine of x cosine squared would give us negative 1/3 cosine cubed x. The integral of sine x cosine to the 4th would give us 1/5, well, negative 1/5, but then we multiply by negative 2, so we have plus 2/5 cosine to the 5th of x. And lastly, minus 1/7 cosine to the 7th of x plus c. Does that make sense? How did I get the 2/5? Good question. So if we take a look at this second integral, we have the integral of sine to the 4th x. Oh dear, that's not quite right. Integral sine of x cosine to the 4th x dx. If we integrated that using u substitution, we would let u be equal to cosine x, then du would be negative sine x. So this integral is negative 1/5 cosine to the 5th x. But then we also have this coefficient out front of negative 2. So negative 1/5 times negative 2 gives us positive 2/5. Make sense? course. All right. And of course, with these trig integrals, there are a lot of the similar, there are several similar trig integrals involving tangent and secant, but this time using the identity that, let's see, secant squared theta is 1 plus tangent squared theta. Yeah, let's actually talk just for a moment about some of these other identities. We have that cosine squared theta is 1 minus sine squared theta. Cosine squared theta equals 1 minus sine squared. Additionally, we have secant squared theta is 1 plus tangent squared. And then we also have the tangent squared. We just rearrange the previous one. Is secant squared theta minus 1. And these are three really important identities for something called trig substitution. Trig substitution is a very powerful tool for integration because it lets us solve integrals that take the form, for example, square root a squared minus u squared, where a is a constant, or the square root of u squared minus a squared, or the square root of u squared plus a squared. And what you'll notice is there's actually a parallel between these trig identities and these three square root forms. If you let a be equal to 1, then what we have is like a 1 is similar to the a squared, so the square root of a squared minus u squared could be similar to taking the square root of 1 minus sine squared theta. In other words, these kind of match up. Same with these two. In fact, we can actually use these similarities to make a clever substitution in some certain integrals to be able to solve the integrals. So let's go ahead and do an example. It's not going to be a terribly in fact, it's one you should already know how to solve. All over the place. Over square root of 1 minus x squared. And that is 1 minus x squared, in case you can't quite tell. This is actually one of our inverse trig rules. So this is equivalent to arctan of x, right? So if we wanted to approach it instead from the point of view of making one of these substitutions we have up here, we could solve it that way. We can see it's of the form 1 minus x squared. So that kind of parallels with this 1 minus sine squared theta. Except in this case, instead of having a sine squared, we have an x squared. So what I'm going to do is I'm going to make the substitution u squared, because you can see right here we have a u squared, and that needs to be equivalent to sine squared theta. Except instead of having a u squared, I actually would like that to say, oh dear. Oh my goodness. All right. There we go. Instead of that saying u squared, I'm just going to have that be x squared. That should be equal to sine squared theta. Then if we take the square root of both sides, that tells us that x is equivalent to sine of theta. So dx is equal to cosine of theta. So if we go ahead and make the substitution, that x squared is sine squared of theta, well then this becomes 1 over square root 1 minus sine squared times dx, which is cosine of theta. That should be times d theta. then by our identity, we know that 1 minus sine squared theta is equivalent to cosine squared theta. So we can actually write that in. On the bottom, we have the square root of cosine squared theta. On the top, we have cosine theta. And then we still have the square root of cosine squared theta is cosine theta. And then cosine theta over cosine theta is, of course, 1. So this is just like the integral of d theta, which is simply theta plus c. But then our answer needs to be in terms of x. So we look back at our substitution we made and see, oh, x is equal to sine of theta. So in this case, oh, I was wrong right up here. That should not be arctan. That should be arcsine. Sorry. Since x is equal to sine of theta, we can take the arcsine of both sides of this equation here, cancel out the sine on this side, and see that theta is arcsine of x. So then we simply go and take x out of this equation down here, or theta out of this right here, and we can see that since theta is arcsine of x, our answer is arcsine of x plus c. Make sense? Let's see. Would you like me to go over another example, or would you like a practice problem now? Another example? All right. So this next example, I think we'll do. Sure. We'll go ahead and do integral of the square root of 16 minus 4x squared dx. In this case, what we first need to do is make sure that we have a 1 where the 16 is. So right here, we need to pull the 16 out of the square root. So we can actually rewrite this as 4 square root of 1 minus 1/4 x squared. And the reason we do that is because all of our trig identities have simply 1 plus sine squared or 1 minus sine squared. We need to have a 1 right there, is what I'm saying. So in this case, because we have 1 minus u squared, that tells us we need to use the identity cosine squared theta is equal to 1 minus sine squared theta. So in this case, we need to match up our 1/4 x squared with sine squared. So that's simply all we do. Let's say 1/4 x squared, all of these, that should be a 1, is equal to sine squared theta. Easy as that. Then we take the square both sides, get that 1/2 x is equal to sine of theta, and I'll go ahead and solve for theta. We get that theta is arcsine of x over 2. And lastly, we need to find dx. So we can say that dx, or x is equal to 2 times sine of theta, so dx is 2 cosine theta. With me so far? Next, we simply make our substitution out for x. So since negative 1/4 x squared was, or I guess 1/4 x squared was sine squared theta, we simply take that out, and we end up with, we can also pull the 4 out, square root 1 minus sine squared theta, and then we have times 2 cosine theta. 1 minus sine squared theta is, of course, cosine squared theta. So this is 4 integral square root cosine squared theta is cosine theta. And if we keep working this through, we get 8 integral cosine squared theta. Then we need to use a different trig identity in order to reduce this cosine squared theta down to cosine to the first power. And to do that, we'll use one of the trig identities I talked about earlier. That was that cosine squared theta was equal to 1 plus cosine 2 theta divided by 2. And if we can take that divided by 2 up front as a coefficient, what happened to the 1/4 in the radical? So what we did there is we actually made the substitution so that it would be taken out when we substituted for sine squared theta. What I did is I said that 1/4 x squared was equal to sine squared theta. So I simply had to take all of this chunk out for sine squared theta. But you'll see that it actually shows up in what theta is solved for, because if we let x squared be equal to sine squared theta, then we would have theta is equal to arc sine of x. But since we have this 1/4, we have that theta is arc sine of x divided by 2. That makes sense? Yeah. And we actually want to make sure we're substituting out this this constant in front of our x squared term so that we can actually use the identity 1 minus sine squared equals 2 cosine squared. Because you'll notice 1. So we need to make sure that it's a 1 when we substitute out. So we were right here with our integral, and that would be the integral of 4 plus 4 times the integral of cosine 2 theta. So that gives us 4 theta plus 2 sine 2 theta plus c. And again, we could take the derivative of this just to make sure. The derivative of 4 theta would give us 4. The derivative of 2 sine 2 theta would give us 4 times cosine 2 theta. And then the derivative of c would give us 0. So this is the correct integral. Next, and our final step should be substituting theta back out. Luckily, we found that theta was equal to arc sine of x over 2. So our answer should be 4 arc sine of x over 2 plus 2 sine of arc sine would simply be the sine and the arc sine would cancel each other out. So 2 sine of arc sine of x over, oh dear, actually, not quite, since we do have this 2 theta inside, it would be 2 sine 2 arc sine of x over 2. In this case, we actually have to be a bit trickier. We're going to need a bit more space out. There's plenty of space over there. All right, I'm actually going to take this all the way over here, up to the top. We got 4 theta plus 2 sine 2 theta plus c. And we also know that theta is arc sine of x over 2. The problem is, if we plug this theta directly into the sine of 2 theta, our sine and arc sine won't directly cancel yet. So in this case, we need to use yet another trig identity sine 2 theta is 2 sine theta cosine theta. So we end up with 4 theta plus 4 sine theta cosine theta plus c. And now we can actually plug in our values of theta. So we end up with 4 arc sine x over 2 plus 4 sine arc sine x over 2 cosine arc sine x over 2 plus c. And here in this spot, this is where our sine and our arc sine will directly cancel. So we end up with 4 arc sine of x over 2 plus this 2 right here. And this 4 will partially simplify to 2x. We still have cosine arc sine x over 2. We still got our plus c. And we are still not quite done because there's one other thing we can do. That is, we can simplify this section here using a handy little trick. If you recall, sine is the opposite angle. So if we have this as theta, sine is the opposite angle divided by the hypotenuse. So we can let this side be, here we have x over 2 inside, and we can actually kind of pair these up with the opposite side over the hypotenuse. This should be an O, sorry, not a 0. So x would be the opposite side, and 2 would be the hypotenuse. Then we can solve for this third side using the Pythagorean theorem. Let's say it's 4 minus x squared. All right. And then from here, we can simply take the cosine of this triangle, and we know that cosine is adjacent over hypotenuse. So the cosine of this triangle would be the square root of 4 minus x squared divided by 2. So what we end up with is 4 arc sine of x over 2 plus 2x times 4 minus square root 4 minus x squared divided by 2 plus c. And lastly, we can cancel these 2's right here. So our final answer is 4 arc sine of x over 2 plus x square root 4 minus x squared plus c. Make sense? So really the thing about trig substitution is it's just a lot of different substitutions, and it can be easy to get confused. So some helpful tips are to write things out in an organized fashion. I like to basically make these columns where I say this is my substitution for this whole chunk right here. I substitute out my 1/4 x squared, and I say exactly what it's equal to. Then right below it, I tend to say, well, what's the square root of that? Because that's what my x is going to be equal to. And I have dx, and I also solve for theta right there as well. That way I kind of know what all my substitutions are, and if I ever forget, I can just look back and they're all in one place. Other than that, some things that'll make it really a lot easier are just knowing your trig identities. Because if you don't know them, these problems get harder. All right, I think we'll give you one practice problem. ahead and try out the integral of x squared minus 25 divided by x. And I'll go ahead and even give you x squared should be equal to 25 secant squared theta. And that means that you're using the tangent squared theta is secant squared theta minus 1. That's the identity you'll be using. And this is your what your substitution should start by looking like. Think you can give it a go? Good luck. How's it coming? Got through the first part. Okay. So what did you get so far? Arcsecant. It is arcsecant. Yep, that's exactly right. All right, let's actually go ahead and start working through this just because I would like to have a bit of time to talk about partial fractions. And trig substitution always sucks up quite a bit of time. But you are on the right track then. So is first we need to simplify this, so we end up with x equals to 5 arcsecant theta. That tells us that theta is just like you said, arcsecant of x over 5. And x. And then lastly, dx secant theta. So dx would be derivative of secant theta is secant theta tangent theta. So dx is 5 secant theta tangent theta. And then we get to make our substitutions. So we've got the integral of square root 25 secant squared theta minus 25. Okay, all over x is secant theta. And we've got dx is 5 secant theta tangent theta d theta. All right, we can start by canceling this secant theta with this secant theta and this 5 with this 5. So now all we have to do is go ahead and simplify this square root 25 secant squared theta minus 25. That becomes the integral of 5 root secant squared theta minus 1. And we still have a tangent theta on the outside. Secant squared theta minus 1 is tangent theta. So 5 tangent theta times tangent theta is tangent squared theta. And just so you know, secant squared theta minus 1, that's tangent squared. Just explain my past steps a bit. I took the square root of tangent squared theta and I got tangent theta. And then tangent theta times tangent theta gives us the and to integrate tangent squared theta, we've actually got to, I'm going to pull out my 5, say that tangent squared theta is equal to secant squared theta minus 1. And actually integrate this if we split it apart into integral of 5 secant squared theta minus the integral of 5. Of course, those both have d thetas. The integral of secant squared is actually exactly tangent, so this gives us 5 tangent theta minus 5 theta plus c. Then, since we had that theta was equivalent to arcsecant of x over 5, well, we know that arcsecant is hypotenuse divided by adjacent. So we have x right there, 5 right there, square root 25 minus x squared. Theta would be this angle right there. And this is just solving the right triangle. So then if we take the tangent of this triangle, that would be square root 25 minus x squared divided by 5. So our answer would be 5 square root 25 minus x squared divided by 5 minus 5 arcsecant of x over 5 plus c. Then we can just simplify a bit more. Our final result is 5 minus x squared minus 5 arcsecant of x over 5 plus c. Make sense? I switched a couple of things around. This should not be root 25 minus x squared. That should be square root x squared minus 25. That's where my mistake was. So these should all be flipped. Our final answer should actually be, let's see, just a moment. Square root of x squared minus 25. Makes sense? In that case, I'll go through a bit of the reasoning behind partial fractions. So, if you remember, when we have just any two fractions, let's say we have 1 over x, and we're adding a second fraction over x plus 1, we can add these two fractions by finding a common denominator, which would be the product of the two denominators. So we can actually express this as 1 times x plus 1 plus 2 times x divided by x times x plus 1. And then simplifying, that would get us 3x plus 1 divided by x times x plus 1. That's just basically how we add fractions together. We can also go through this process backwards. Let's say we start with the fraction 3x plus 1 divided by x. We can actually use this process backwards to say, well, it must be the product, or sorry, the sum of two independent fractions, each with one portion of this denominator, because this is the product of two separate parts. We can write this in this form and see, well, if you were to add a and b, these two fractions together, what it would end up with is a times x plus 1 plus b times x divided by x times x plus 1. And that would have to be equal to our original fraction, 3x plus 1 divided by x times x plus 1. Then if we multiply both sides by x times x plus 1, our denominators just cancel. And what we're left is an equation, a times x plus 1 plus b times x equals to 3x plus 1. But then this equation should hold for any x value, because this equation holds for any x value. So what we can do is we can solve for a and b by plugging in specific values of x. So let's say first we wanted x to be equal to 0. We have a times 0 plus 1 plus b times 0 is equal to 1. So 1a is equal to 1. So then we know that a should be equal to 1. Next, we can plug in negative 1 for x, since that'll cancel our a term. And what we get is b times negative 1 is equal to negative 2. And what that tells us is that b is equal to 2. And then if we simply rewrite a and b, take a and b out of this original we got, what we see is we have 1 over x plus 2 divided by x plus 1. And that was equal to our original 3x plus 1 divided by x plus 1. And what you see is this is actually the exact result that we started with when we simply added the two fractions to get this 3x plus 1 fraction to begin with. So that's kind of the basic principles behind partial fractions, is you want to split apart your denominator into 2 or possibly more different fractions, and then you simply let there be constants in the numerators of those fractions, and then try and write out an equation like this that will let you solve for what those constants should be. I'll go ahead and do another example. This one's going to be a bit more complicated. So let's say we start off with of 2x plus 3 divided by x times x plus 1 squared. Well, first we need to figure out what all the terms on our denominator are. First off, we've got an x term. Next, we have an x plus 1 term. But then, since this x plus 1 term is repeated, we actually have to say that there's a third term specifically for x plus 1 squared. Then, we need to say, well, in order to make this first denominator equal to this common denominator of x plus 1 squared, we would need to multiply a over x by x plus 1 squared divided by x plus 1 squared. We have a times x plus 1 squared as a thing to note, I guess, is we typically you could actually go through and combine all of these and cancel the denominators, but typically we skip that step because we can skip straight to writing out an equation using just the numerators because the denominators cancel. So what I'm saying is a times x plus 1 squared, then we have b times x times another x plus 1, because that's what will get this denominator to be the common denominator. And we have plus c times just an x. And then that should be equal to the numerator of the original fraction. Then we can simply plug in some x values. We'll start with x is equal to 0. Then 1 times a is equal to 3. So a equals 3. Next, we can let x equal to negative 1. Then negative c is equal to positive 1. So c is equal to negative 1. And lastly, we can plug in, well, actually, lastly, we have a couple of options. We can either plug in another value of x and then use the values of a and c that we've already found, or we could try and match coefficients of this equation. So if we distributed x in this x squared plus 1, you'd see that we've got an a times x squared term. And in this case, I'm only going to look at the x squared terms. In this b term, we have a b times x squared. And then we don't have any x squareds for c or anything on the other side. So we can kind of write like a mini equation and say that ax squared plus bx squared is equal to 0x squared. That tells us that a plus b should be equal to 0. So since a is 3, we know that b should be negative 3. And then we found our three constants. So we just take this and write it out. And our final answer, since a was 3, we end up with 3 over x plus b was equal to negative 3. Negative 3 over x plus 1. And lastly, c was equal to negative 1 as well. So minus 1 over x plus 1 squared is our answer. Any questions?